All right, first circuit problem here. We have an RLC circuit. I is the current. This equation is one that we use, that Li double prime plus Ri prime plus 1 over C times I is equal to E prime of T, where we got these electric numbers and coefficients from different things in the circuit. E is the voltage at any given time. And take a note that here E of T is 100 volts. And on this right side, we get E double prime of T, or E prime of T. Let me hold on. There, I've written it out here. E of T is 100. So E prime of T, well, I derive that and I get 0. That's nice, because it gives me 0 on the right-hand side of my differential equation, and I don't have to do undetermined coefficients or some other method like that. So this one is pretty pleasant, well, for an electricity problem. All right, so let's go ahead and see what we have here. We have L, which is 0.01, so that gives me 0.1 I double prime plus, all right, R is 50, I prime, plus 1 over C. So I got 1 over 0.0005 I is equal to E prime of T. That's this right here is 0. So couple things. We can do 1 divided by 0.005 in a variety of ways. That's going to give us 2,000. Yep, 2,000. And then the next thing that I want to do is, in the earlier differential equation stuff, we will call it normalizing, where we make the coefficient of the I double prime, the biggest derivative, have 1. So in order to do that, I'm going to multiply by 10 everywhere. That gives me I double prime plus 500 I prime plus 2,000 20,000 I is equal to 0. To me, it's more pleasant. I make less mistakes if I have a 0 or if I have a coefficient of 1 here. You could totally do everything with it as a 0.1. So from there, characteristic equation, R squared plus 500R plus 20,000 is equal to 0. So there are a variety of ways to do this. One way would be to use quadratic formula. Another way would be to try to factor. Going to be some trouble here. We could also graph it on a calculator and find the intercepts. I'm going to go ahead and complete the square for this because I like completing the square. Completing the square is nice and clean to me. So R squared plus 500R plus, all right, I'm not going to show the work. I divide 500 by, I guess I'll write it. 500 over 2 squared. If you do that on a calculator, you get 62500. So that's what I'm going to write here, 62500. And then equals, all right, this 20,000 is going to get moved over to the right side. Actually, I guess I'll write it. So minus 20,000. And then I added this 62,500. So I'm going to add 62500 in order to balance the equation. That on the left side factors to R plus half of the 500. So that's R plus 250 squared is equal to, when I combine these terms, I get 42500. And then I can square root and move the 250 over. That gives me R equals negative 250 plus or minus the square root of 42500. This is about negative 250 plus or minus, 206.155. Now, if you do that, one of those is going to be negative 0.845, and the other one is going to be negative 451.155. So, like I said, you can use whatever method works best for you in order to get to those two numbers. But those are the roots of our characteristic equation. So from there, we need to, I should mention one little thing here. In reading the original problem, you can see that I get an initial current and then an initial derivative of the current. So what I need to do is, this is an initial value problem. I need to solve for my C's. So what we're going to do is take those two decimals that I got, and maybe we'll change colors to purple. I get that x is equal to C1 e to the negative 43.845 t plus C2 times e to the negative 451.155 t, like that. Now, let me zoom in a little bit so it's easier for me to write. Now, I know that I've got my two initial values right here. That one has the derivative. So I need to find x prime, which is negative 43.845. This is chain rule. C1 e to the, man, I have to write this a lot, negative 43.845. All right, there we go. So I got this as the chain rule there, and this as the chain rule here. So now you can see I of 0 is 0, and I prime of 0 is negative 75. So I've shown in my videos here how to do the matrix work, and I'm going to do this quickly. So the top row in my matrix is going to be a 1 and a 1. That's from plugging in t equals 0 to this and t equals 0 to this. I just get C1 and C2. And then I get a bar, and then I get my negative, or sorry, I get my 0 over on the right-hand side. This right here, this line, is x of 0 equal to 0. Plugging in t equals 0 to this, and then using the initial value that we're given. The next one is going to have that 75, and it's actually negative. And then when I plug in t equals 0, again, these guys, all those terms there, including the e to the, well, the e to the is going to be e to the 0, and it's going to get a 1. So what I wind up getting is negative 43.845 and negative 451.155. So this is where, again, my calculator it makes it so much easier. So you can REF it. You can do this by hand if you want. Totally up to you. With those decimals, I much rather prefer to use the calculator to REF it. All right, so pop to the matrix on our calculator. Go over to Edit. We're going to make A a 2 by 3. You can see I've already put it in here, 1, 1, 0. The negative 43 mess, and then the negative 456 mess, and the negative 75. So quit, second, matrix, math, roll around the top to our REF, and then pull up matrix A, hit enter. Boom. I get these two numbers right here, 0.181 and negative 0.181. Actually, 0.182 if we round up because of that 9. So this is my C1 value. This is my C2 value. So my little arrow, I'm going to make it go like that. I'm going to write RREF so I indicate how I got that. And all I have to do then is take these two values and put them in here. So my final solution is going to be x equals negative 0.182 e to the negative 43.845 t plus 0.182 e to the negative 451.155 t. Before I go any further, we'll box this. That's my answer. Check. I'll just comment that I typically like to have fractions if I can have them, if they're accurate. But as soon as if I zoom out all the way and we look at this whole problem here, as soon as I square rooted this number, this 201 or 206.155, that was irrational. Didn't have a fraction for it. So everything else that follows that is stuck in this irrational zone. So this is a problem for which it makes sense to use decimals, and I typically like to just round to 3 decimals because that works for me in my math brain. So hopefully you're okay with these RLC circuits when we have a constant energy battery input, whatever you want to call it, into this system. In the next one, we'll do one where it oscillates as if it was plugged in to the wall.